Like what things did you notice, or like what, like about it? So before you answer that, I kind of alluded, I believe is the right word, to this on Friday. This is straight calculus. This isn't like engineering calculus and everything. So we need to deal a lot with the theory. Okay, and so I've kind of said this before, but this book is going through, and you're building as you go. So we needed to take care of limits so that we can start talking about derivatives. And we needed to talk about limits so that we can talk about the integration, which is the other word for accumulation. And so now that we have that, we're able to advance our way through. Okay, so now, some things should have been very familiar, and then others maybe not so much. So anything in particular?
We talked about how derivatives and the tangent line or instantaneous rate of change are related.
Okay, so
like a derivative, it says like that it is the function for the tangent line as it changes along a curve.
Okay, so the first thing to get out of what you just said is that we are going to create a derivative, which is a new function. And we're going to do that theoretically, and then we're going to start looking at some easier ways to go about it. And again, like this is kind of what I said before. Once you establish something in math, then you can use it, and then that usually means it's going to get easier. And so the very first thing that a derivative is something that we've already talked about, right? It's the slope of the tangent line. And do we remember what a tangent line looks like?
A line going through a curve.
So 1 point through a curve, so it's only touching it at once. And so like if you zoomed in here, it's not sharing this for a long period of time. It's just hitting 1 point and going on. Okay, so it is directly related to that, and which means that it's kind of related to the secant lines. Okay, so yes, we are going to create a function called a derivative. And the values of that function, of that new function that we've created, are going to be, theoretically, the slope of the tangent line. What that does for us is it allows us to make the connection between the slope of a tangent line and the instantaneous rate of change, right? We started off with speed, which is a rate of change. And then we said, okay, the average speed is just finding the slope. The instantaneous is like if you're looking at your speedometer. But again, this applies to anything that's changing. And if you read those first couple paragraphs, like they talk about like how everything is changing. And so then if you can analyze the change, then you can figure out all kinds of stuff in basically everything. So like essentially everything that is in our world right now has to do with calculus. Right? There is no flying without calculus. There is no computers without calculus. There is none of this stuff, okay? So it does apply to anything that's changing, you can apply calculus. And then you can find the actual instantaneous rate of change of whatever we're talking about. Okay? So if you guys are having a note, hopefully you have like a place that you're keeping some AP stuff. Okay, so we're going to talk about that. So the first thing, like I don't know if you need this one in there, but it's kind of like what we just said. We identify the slope of the tangent line with the instantaneous rate of change. They are interchangeable. They are exactly the same thing. Okay, the slopes of the tangent lines as they change along a curve are the values of the new function. So we're going to create a function. We're going to be able to take that function and plug values into it. And so like if you're looking at this curve right here, this parabola, let's say this is 5. Once we have the derivative of this formula, we could plug 5 into it and find the actual tangent slope at that point 5. Okay, so that's a very important thing to keep in mind. You're creating a function, and it's evaluated the same way any other function is evaluated, but the output is telling you something very specific. It's telling you the slope of the tangent line at that point that you plugged in. Is that okay? So again, I would definitely have something that is a place that you can read through and understand quickly. I'm doing right now. I don't want to do anymore. All right, here we go. All right, so now, as you guys are writing that down, and then you definitely want this thing at the top of the next page, and then I'm going to talk to you while you're writing that down. So I am able to, like, after you guys take your AP, I'm able to get a bunch of information back, and it kind of highlights things that went well and then highlights things that didn't go so well. So, like, referring to last year's, they did super awesome on limits, and I expect you guys to do the same. And then they did super awesome on a lot of the derivatives and things like that. But one of the things that we struggled with was the idea of the relationship between velocity and acceleration and velocity and position. And so that's one of the things that I want to try to really work on this year. And this top thing on this next page, where page this is, I think is going to really help in the understanding of what that part is. So if a curve represents the trajectory of a moving object, okay, so a very specific thing. So this would be like the position. The line tangent to the curve, which we will call the derivative, at a point, gives the direction of the motion of that point. Okay, so that's going to help you keep some things straight when we talk about velocity. Okay, because all velocity is speed and direction. So if we're traveling up on our position, right, that tangent line is saying, oh, that's the direction that we're moving. Okay, and so that should definitely be in your notes, because that's going to be one. So again, we're going to, each of these things that we talk about individually are not the worst thing in the world. But when you start layering them on top of each other and then having to remember, a month ago, 2 months ago, 3 months ago, that's where things get very, very challenging, okay? And so just rereading that, especially once we start talking about it, that's going to, I think, help you a lot. So now, what we have over here is something I should look very familiar. This is kind of like the first thing we started with when we were talking about limits, okay? And, we have these basically slope formulas that keep popping up and popping up. Okay, so this is going to lead us into our definition of derivatives. So, what we had here was a bunch of secant lines. And again, if you're just plugging in the slope formula for each of these secant lines, P to Q, then, right, all you're doing is finding the slope of each, and that represents the average rate of change. Again, very important, because again, we're going to deal, most of this class is going to be instantaneous, and then every once in a while they're going to throw in the word estimate or average, and probably you're going to either just do instantaneous, or you're going to be like, did we even talk about this? I don't even remember, okay, because it's going to be such a brief thing. But that's going to be like one of those questions that should be a gimme, because that just means you're just using the slope formula, okay? But anyway, as we shrink up the distance between A and X, then what we're doing is getting closer and closer and closer to instantaneous rate of change. We're no longer dealing with the average rate of change once we get to the tangent line. So two separate things, and you will be asked about both of them. So if we're okay with just using the normal slope function for P to Q, explain why once we add the limit, so, right, the distance, right, is change in y over change of x. So the change of x, right, is from x to a. That's what that's saying down there, right? We have a point x and we have a point a. And so part of the average is when we have this distance down here. So then y, can you explain why? As we get closer and closer, as those two values basically become 1, why is this now an instantaneous rate of change, or a tangent slope? Because that's basically what the limit is saying, is we're getting it down to 1 point. We're shrinking it up and shrinking it up and shrinking it up until essentially it's just 1 point. And then there it is, there's the instantaneous rate of change. Okay, so all of this is basically, in a way, saying what I'm saying. And so then if we get down here to the bottom, here's our first definition. Rate of change, right? Rate of change and the slope of the tangent line. Right? The average rate of change is right there. Once you throw the limit and shrink up that denominator, shrink up the distance on the x-axis to nothing, then we're finding the instantaneous rate of change. And this is why we needed limits first. Because again, calculus is about instantaneous rate of change. So we needed to have limits just to be able to think of that. And then down here, and you guys are going to see this little equation like a million times as an exaggeration, but this is just point slope form of a line. But it's going to be very important for us in a couple different sections. Okay? So average rate of change, instantaneous rate of change, the slope of a tangent line. Or I'm sorry, the equation of the tangent line. So far, so good? All right, so then let's do a homework problem. So you guys are doing 9 through 35. 9 through 35 odd. So should we just do 9 together? So I'm gonna shrink this thing up so we can still kind of see it. I'm gonna put it over here to the side. All right, so then I'm just reading the directions. It says use definition 1, which is the one we just talked about. So we're talking about f of x and f of a, okay? To find the slope of the line tangent to the graph at P. Okay, so then here's what we have. We have number 9. And they gave us f of x is x squared minus 5. Are you guys offended that I'm doing your homework? Okay. So we are being asked again to find the instantaneous rate of change at this point. So that's part A. So then we are using, right, we're using this limit formula from this section 1. Because we want the instantaneous rate of change, okay? So then I'm going to copy it down. Well, I'm not going to copy it down since it's sitting there. But let's fill some of this in, right? So we're doing, right, the limit as x approaches what? So it's going to be specific for each problem right now. So what is A according to this problem? Say. Right, so we're talking about x values here, right? We're creeping closer and closer on the x-axis. So then 3, yeah. So as we get closer to 3, right, we're shrinking up that distance. We are going to take the limit of, right, f of x. Okay, so then we're going to take the limit of x squared minus 5, right? That's x. That's f of x minus. So then what is f of a here? So it'd be 4, right? Because you can just plug 3 in. Or in fact, they give it to you on this one, right? They actually give you that. But you do need to find it. So f of a is actually a number. So remember, anytime you see a, you're thinking of an actual number. X is just an x. Okay, so then we're going to subtract 4 from that. And then it's going to be over x minus 3. So, you know, this is kind of like a refresher. Oh, and we can simplify this down, right? Let's simplify this down a little bit. So then we go in like this. So firstly, does everyone understand why we're setting it up like this? And what we're actually finding? So again, good questions if you got them. So again, we're trying to find the slope. That's what we're finding right now, the tangent slope. That's what we're finding at this specific point for this specific curve. Why, what's the problem right now with what this statement says? You're going to get a 0 over a 0. So now we got to use our factoring rules. Okay, so that's x plus 3, x minus 3. And so then is it okay, since I'm running out of a little bit of room, is it okay if I just write it like this? So then we're left with x plus 3. And so now we can just evaluate that. So at that specific point, not any other point, okay, but at that specific point on this curve, the slope of the tangent line is 6. So far, so good? So then part B, it says, determine an equation of the tangent line at P. Well, we're just going to use point slope form. So then y minus 4, right, that's what f of a is, equals 6 times x minus 3. Now in the back of the book, I think they often solve for y. So when you check, keep that in mind. On the AP test, you could leave it like that. That's, as far as I can tell, that's fine. But in order to check, right, it's going to be y minus 4 equals 6x minus 18. And so then y equals 6x minus 14. And
What are you pointing this into?
so this is the point slope form. So we're going through, so like we have this parabola, right? And it looks something like this, okay? And so then what we're saying is that if we, so what you guys can do, and this is part C, is you can graph the original function that you're looking at, and then graph y equals 6x minus 14, and it should give you something to the effect of like a tangent slope somewhere over there. Is that okay? Now, if we wanted to find another tangent slope and we're doing it this way, we'd have to re-go through that process. So we're only finding one place, one tangent line in one place. So far, so good? Any questions? Again, this is like the beginning, so questions now are super good. So anything that you're not sure about?
So part C is this bar?
So part C on this, well, part C is just like graph them so that you can see it. But the where we're getting that line, is just point slope form. So right.
And then part B is that?
Yeah, that's part B. So you're just doing y. So remember, like it used to be y minus y1 equals m parentheses x minus x1. That's like what we saw point slope to be before. And so now they're just saying, well, it's at this. We're talking about the point is a f of a, and so that's how they're writing it there. Is that okay? All right, so this next part is like what I was telling you before. You're going to get this kind of question on the AP. And the goal is to remember that we're just talking about slope. And what is slope basically? It's y2 minus y1 over x2 minus x1. And so that's what we're talking about all the time. When we're talking about derivatives, we are always talking about the slope just in a limit form. But if you look at because there's only one of these questions, but again, you will get this question, and just do you remember that it's about slope? That's the question, okay? But I want you to see what it's saying here, and this is the key. All right, so Facebook, The following table gives the number of daily users of Facebook averaged over each month shown. Estimate, there it is. Just do the slope formula. Okay, as soon as they say find the average, or as soon as they say estimate, you don't have to worry about the derivative. You're just doing the slope formula. And they say, okay, so estimate the instantaneous rate of growth of Facebook users for June 2011. Okay, and then they say, what are the units of your answers? So you remember when you're doing those free response, actually the units are a full point. Okay, so if you're going through these things and you don't know what the heck, if this is the right answer or not, if you put your units on there, you're getting a point. Okay, so always put your units on. And so that's just y per x, so just so you understand, okay? All right, so then they're saying, okay, so instantaneous, oops, that's not what I wanted. Instantaneous here. And so basically they're going to show you 3 ways to think about it. And none of the, well, there is one that I think is better according to the AP. But in the book, they're going to ask for 3 different spots. So you could do the slope formula with June 2011 and March 2011. Okay? So, right, so then the X's are the month and the Y's are the daily users. You could also do, for an estimate, you could do the slope formula for June 2011 to September 2011. And then your third option would be to do like, to estimate June would be September 2011 and March 2011. Usually on the AP, you want the 2 on the outer side. And just so like you get on the AP, they probably wouldn't give you June. And so it would be kind of like a little bit more of a hint. You would just like do March and September because it's on either side. But you're just doing the slope formula 3 times. And then would it make sense that, oops, right, because they want the units of your answer, right, would be like millions of daily users per month. Does that make sense? And so then what you can see, and this is why calculus is nice in like business settings and things like that, they can actually, so what they're saying is that each month is an instantaneous place. So they could actually, using this formula, they could give a relatively accurate idea of how fast, how would you say it? Is the daily users increasing or decreasing during this month, and how fast? Because then they can make decisions on that. Right? If it starts slowing off, right? If you're Facebook, it's like, we better put more misinformation out there so people start clicking again, right? Or whatever they do to ruin everyone's mind. But does that make sense? But that is what they do, by the way. All right. So, how are we doing on time over there? 18 minutes, so we're doing good. Okay. So we did the first version, from one point X to one point A. Shrink it up, shrink it up, shrink it up. Now we're at an instantaneous rate of change. So now all they're saying is, like, what if we just change our notation? And we're still concentrating on some point A, and then we're going down the x-axis a little bit, okay? And so now we're just adding a little bit more. That h is just like this little itty-bitty number that we're adding. Okay, when we're kind of far away, we have a secant line, it's an average. As we get closer, that average gets closer and closer to the actual instantaneous. Okay, but since the denominator is the distance, is it okay that it's h? You know, and mathematically, right, that would be, over a plus h minus a, right? And that's how the a's cancel, and that's how you're just left with an h. So it's the same exact statement, just different notation. Why? because sometimes it's easy, like that first one, you just factored, no big deal. Sometimes it's not so easy, and so this may look or seem a little harder, but that depends on the problem, which one would be harder. Now, they're going to just tell you to do one or the other. In the long run, it doesn't really matter, except for one specific thing that I don't know that I'm going to mention today, but I'm going to mention tomorrow, okay? But for the most part, they're just going to tell you which one to do, and just assume that that would be the easiest way to do it. So then nothing is different now. Okay, we just have a different definition. So we still start with the slope is the average. Okay, as we shrink up that distance, as that little bitty distance h that we're looking at, as that gets closer and closer to 0, then we're going to say that's instantaneous. And then they're going to say, okay, that's the slope of the tangent line, and we're still going to be asked to come up with the equation of that line. So then we can jump down to, we'll do number 17. All right, so 17, right, it's basically the same thing. We're just using f of x as 2x plus 1. And then we're going to, this value, we're going to go 0, 1. That's the point. All right, we're doing good. We're doing good. All right, so then what we're doing then is the limit, as now we're talking about h approaching 0. So that distance is going to 0. The distance on the x-axis is going to 0. Then we're doing f of, what's a in this case? Oh, I kind of don't like that they're doing it that way. Oh, that's too bad. All right, so I don't want you to think it's the same thing. So f of a, right, so a is over here. I wish I wouldn't do that. A is this. A is 0. Is that okay? That is not what this 0 is about. Is that okay? So don't, when you're doing the homework, don't get mixed up. You're always going, h is always going to 0 right now. Why? Because that's, h represents the distance you're moving away from the x value. Here, let's do it. Let's just do it different. Let's do, yeah, let's just do 19. How did I get rid of this? Yeah, I don't want you guys thinking that's what's going on. Hold on. Let's do this. All right, so then 19 instead is x squared minus 4. And then our point is 2, 0. Okay. All right, so again, we are always going, in this version, right, different version. In this version, we're saying that that distance is 0. It's always going to be 0 because we want that one little point right there. Is that all right? All right, so then we're going to say f of a plus h is really, in this case, I'm going to write it out this time, as 2 plus h. Minus f of 2. We'll write all the way out over h. Is that okay? Now we know what f of 2 is. It's in the point. And you can plug it in because on the next section, hopefully we get to one of these. Like they're not giving you the actual point, so you got to go find the output. They're still giving you the input, okay? So in this case, we know that f of 2 is 0 because they've already done it for you. Or you can just plug it in and it'll still be 0. So then what this next part is, oops, I ran out of room here. So then the limit as h approaches 0, as that distance gets smaller and smaller. And so then what we're doing is, what is it, x squared? So then 2 plus h squared minus 4 And so that's all f of 2 plus h. Is that okay? That's f of 2 plus h? Okay, then minus f of 2, which is 0. So again, right, the problem ends up becoming, when we try to evaluate this, is if we try to direct substitute, we get 2 squared, which is 4. 4 minus 4 is 0. Over 0, 0 over 0, we can't do anything, right? So now we have to go through some of our things. And so the first thing I'm going to do is simplify the 2 plus h squared. Okay, so then that's going to be 4 plus 4h plus h squared minus 4, and that's all over h. Now, is that okay if I do that? Right, you got to FOIL that out. And so then what we have, after we simplify a little bit further, so now we're going to take out an h, right? We're going to factor out an h. And so then really what we're taking is the limit as h approaches 0, and I'm just doing it to save room, of 4 plus h. Is that okay? And now we can direct substitute in, and we get 4. So that was part A. Use the definition to find the slope of the line tangent to the graph f at P. That's just what we did. Determine an equation of the tangent line at P. Okay, so then, right, we have a point, and we have a slope. So then that's part A. So part B, right, would be y minus 0, right, because that's that was the y value, equals 4 times x minus 2. And so then in the back of the book, they're going to have this. Oh, we're doing good. Good. As long as you guys are understanding right now, we're doing really, really good. You guys, everybody okay? Okay, so again, you're taking a derivative right now. This is totally the obnoxious way to take a derivative, and you won't do it very often, but we're taking derivatives right now. Welcome to derivatives. This is all what a derivative is. Instantaneous rate of change, which is the same thing as the slope of the tangent line at whatever point we're looking at. Okay? All right, so that's that. That's that. All right, so we got to get a little bit further then. The rest of this, so just to be clear, all we've done is at one single point. And in the long run, which I guess is right now, we're going to create a function so that we can just plug in values and get the slope out right away. Okay, because who wants to do that for every single point? Okay, so you just want to have a function that you can plug it in and get somewhere. So we're looking down here. So the derivative function itself. Okay, so basically that's what I said. Okay, so here's some things that we want to keep straight. Okay, you want to be able to identify a positive rate of change, negative rate of change, and 0 rate of change. Fair enough? So remember, we're going left to right all the time. So going left to right, as a function increases, all of the instantaneous rates of change are positive. Now they keep slowing down until they get to a hill or a valley, depending on which way you're going. And then that's going to be an instantaneous rate of change of 0. So think of throwing a ball up in the air. It slows down, and then it starts coming back down. So it has to get to zero. You can't change directions without first going to zero. And then going left to right, if we're decreasing, all of those rates of change are negative. Fair enough? Okay? Because we're going to talk a lot about that kind of stuff. All right, now we're talking about notation stuff. Okay? This is the notation. If you see f prime, that's f prime. Okay, they're talking about a derivative. You got to know that. You'll know it because we're, Okay, so now they're saying two different things here. Okay, first they're saying if we want the derivative, which is what we've already done, we could have labeled it, we could have notated it this way. Then you would say the derivative at a specific point, is just what we did over here. Fair enough? Okay. Okay, but, oh man, that's all blurry. But, if we just say, well, we're not doing it at a specific point, if we're just doing it for all x, we're using the same stuff, except notice that there's nowhere where we're plugging in that one point. Then we're actually going to create the derivative function itself. Okay? So, in order for me to get through this example, like, this has to be in your notes and this AP thing, but don't do it now, we'll do it tomorrow. This has to be in there, and there's going to be something I'm going to tell you about the AP stuff later. Okay, but just to save time, because we got 10 minutes? 5 minutes, that's barely enough. Okay. So how about this then? Since it's only 5 minutes, I put down a certain thing. Let's just go to, 9, 9 to 35 still works. Oh, why is that trying to go further than that?
Well, below the derivative function at the bottom of that page, it says 27 to 40.
Okay, so let's just do 9 to 25 then. Yeah, okay. I think you guys can get to 35, so if you got some extra time, they don't want you switching to the other way till 37. But if you have some time, so you can do more, but get up to 25, and that's good, okay? And then we'll start there tomorrow.